Aloha! Today we're going to continue looking at limits at infinity. We're going to first take a quick glance at some laws for limits at infinity, and then we're going to focus on how we can find limits at infinity of rational functions, because there is a neat trick that we can use there without having to make any tables of values. But let's start by jumping into some limit laws. And here we have them. Some of these are very similar to the regular limit laws that we saw for limits that weren't at infinity. And so I want to go through some of these relatively quickly. First of all, this is very similar to what we saw with regular limit laws. The limit of a sum or a difference or a product or a quotient is the sum or the difference or the product or the quotient of the limits. If we have, for example, the limit of a sum of a bunch of terms, we can evaluate those limits term by term and then add those limits together. Same thing is true with differences, with products, with quotients, so long as the denominator isn't equal to 0, of course. Right? We also have that the limit of a constant times a function is equal to the constant times the limit, meaning if we have a constant multiplier inside a limit, we can just pull that constant out of the limit and evaluate the limit of the rest of the function. We have a few more. The limit as x approaches infinity of a function to a power is just the limit of that function as x approaches infinity raised to that power, so long as that limit exists, of course. There are situations where these limits don't exist, or we have a 0 in the denominator where, of course, these things aren't going to be true. We could spend 5 times as much time and go through these really slowly and carefully, but I think most of these are unsurprising, especially these first ones. So I just want to get them out of the way pretty quickly so we can focus on the rational functions, which are really interesting. The next rules say that the limit of a constant function as x approaches infinity is just equal to that constant, which should make sense. A constant function is a horizontal line, so the function is always equal to c, so of course that is the limit. Also, the limit as x approaches infinity of x is infinity, which I think should make intuitive sense. As x approaches infinity, what's happening to x? It is approaching infinity, so the limit is infinity there. These last two are a little bit more specific, and we're going to be using them with rational functions. If r is greater than 0 and is a rational number, then the limit as x approaches infinity of 1 over x to the r is equal to 0. So remember, whole numbers are rational numbers. So if this was 1 over x squared or 1 over x cubed, or 1 over x to the 4th, the limit as x approaches infinity is 0. I think that makes sense because the denominator is growing as x grows, and when you've got a fraction where the numerator is constant and the denominator is growing arbitrarily large, that value is going to get closer and closer to 0. And this is true for all rational values of r greater than 0. Even if r is 1/2, that's 1 over the square root of x. That also has a limit of 0. Same thing with any positive rational value of r. And then similarly, if we want to look at the limit as x approaches negative infinity of a situation like this, the limit is still equal to 0 so long as we choose a rational number such that x to the r is defined for all x. If, for example, you chose 1/2 for r, the square root of x, that is not defined for negative numbers, so then of course that limit would be undefined because x could not approach negative infinity in that case. It's just always undefined. So this clause here is just to make sure we're not taking any even indexed roots of negative numbers. All right. We're not going to dig too deeply into these, but we will use a couple of these in our methodology for looking at the limit of a rational function as x approaches infinity. And I want to look at an example right now. Here we want to evaluate the limit as x approaches infinity of the rational function 3x squared minus x minus 2 all over 5x squared plus 4x plus 1. Now what we're going to do here is we are going to rewrite this, the limit as x approaches infinity. But in the numerator and denominator, what we're going to do is we're going to divide them by x squared. And so in this numerator, we're going to have the 3x squared minus x minus 2 divided by x squared. And then the denominator, we're going to take 5x squared plus 4x plus 1 and divide that by x squared. Now this is only problematic if x squared equals 0, because we can't divide by 0. However, if we're looking at x approaching infinity, we are looking at large values of x, so that is not a problem. And so, once we do those divisions, we have the limit as x approaches infinity of, and then in the numerator, 3x squared divided by x squared is 3, and then minus x over x squared is 1 over x, and then minus 2 over x squared is just 2 over x squared. We're going to do something similar in the denominator. 5x squared divided by x squared is 5. And then plus 4x divided by x squared. That's going to be 4 over x, because one of those x's cancels. And then that last term down there is going to be 1 over x squared. Now, at this point, we're going to use some of our limit laws. We know that the limit of a quotient is equal to the quotient of the limits. So we can split this up into one fraction where we've got limits in the numerator and denominator. So we've got the limit of 3 minus 1 over x minus 2 over x squared over the limit of 5 plus 4 over x plus 1 over x squared, both as x approaches infinity. And then we know that the limit of sums and differences is the sums and differences of the limits, so we can evaluate the limits of each of these separately. So it's going to be a lot of limits. It's going to be the limit as x approaches infinity of 3 minus the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 2 over x squared. And all of that is going to be over the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 4 over x plus the limit as x approaches infinity of 1 over x squared. And then we can evaluate each of these limits. The limit of a constant as x approaches infinity is just that constant. So that first term is going to be 3. And then minus, if we look at 1 over x, that falls under this rule. That's 1 over x to the first. And so that limit is 0. And similarly, this limit is also going to be 0. You could pull the 2 out front if you need, but the limit of 1 over x squared as x approaches infinity is 0. So we've got 3 minus 0 on the top. And then on the bottom, with similar logic, we're going to have 5 plus 0 plus 0. And then this becomes 3/5. Basically, our strategy is that when we're looking at the limit of a rational function as x approaches infinity, we want to take the largest power of x that occurs in the denominator and divide the top and bottom by that power of x. And what that's going to do for us is it's going to give us a denominator where the first limit is going to be a non-zero number, And then the other limits are going to be zeros because those degrees are smaller. So we're going to end up with these sorts of fractions where we know the limit is 0. And then in the numerator, you might get a term that's a non-zero number in addition to other zeros. They might all be zeros, in which case it would be 0 over 5, which was 0. It is also possible that in the numerator, you end up with something that has a limit that is infinite. And in that case, an infinite limit over a whole number, positive whole number like that is just going to be positive infinity. If this was negative, it might be negative infinity. But basically, by dividing by the highest power of x in the denominator, we end up in a situation where we've got a bunch of zeros and then some individual terms that we can evaluate, which is much easier than just trying to look at the whole polynomial and maybe making a table of values or something like that.